So let's put some numbers in it. And these are not numbers that come from academic papers. These are numbers that come from us working with suppliers, with existing things that can be bought at the market at scale. This is to produce 1 gigajoule of fuel, call it 30 liters. This is a lot of numbers. Let me simplify it a little bit. Let's go to efficiencies. This shows you, first of all, the end-to-end efficiency of turning electricity into fuel, 44% for these particular set of numbers. On the one hand, you should think that's terrible. Batteries, after all, have round-trip efficiencies easily of 90%. But I think the big lesson is that round-trip efficiency is not all that matters. As solar PV gets really, really cheap, the ability to take it and make a fuel, which is easy to store for years in huge quantities, easy to transport with existing infrastructure, that is huge, and that can, in some markets, trump the efficiency disadvantage. Plus, there are ways that we can certainly improve on that. This is all with existing technologies. People can figure out how to do better. This shows you the breakdown of the different energy uses in that plant. So you need about half of the total electricity to make hydrogen, about a third of it to make the CO, and in this particular version, about 17% is what we need for carbon engineering to do the CO2 from the air. That reflects something. A lot of people have worried that our plant, carbon engineering's plant, is too energy intensive. We deliberately designed it not to focus on energy efficiency, but to focus on low technical risk and low capital cost. And I think this kind of breakdown shows you that our energy use is not the big deal. Yeah, we could be a little bit better, but what really matters is cost. We're interested in bringing this to market at commercial scale in the real world. So let's think about what the 44% means when you turn it into energy units and do the math. That means when we get to $10 a megawatt solar, and it's going to happen. We can argue if it's 2030 or 2035, whatever. That means that the cost of that solar electricity would only contribute something like 27 cents a liter to fuel. Now, of course, overall fuel costs are going to be higher than 27 cents a liter. So currently, our carbon engineering system would contribute about 20 cents to those costs. And based on current or emerging technologies, we think it's reasonable to bring air-to-fuels to market at something like $1 a liter in the mid-2020s.